Okay, so this first section covers preliminary theory for linear equations, and it's broken into 3 parts. So we're going to do the first part now, and then tonight you all will watch the video for the second part. We are going to start by focusing on what's called an IVP, an initial value problem. So an initial value problem. The ones that we're going to be looking at are the following. An of x times the nth derivative plus a n minus 1 of x times the next derivative, so on and so forth, down to a1 of x dy dx, a0 of x y is equal to g of x. So that we've seen before. This is just a plain nth order linear equation. If it's nth order, in order to find all of the constants, we will need n conditions. So we're going to have an equation like that is subject to the following initial conditions. We have y of x naught is equal to y naught. And then we have the derivative at x naught is equal to y1. The second derivative at x naught is equal to y2. All the way up to the n minus 1 derivative at x naught is equal to y of n minus 1. So hopefully we can tell here there are n conditions. So again, nth order, we're going to need n conditions. So what we are doing is we are looking for the solution or a solution that contains that value x naught on some interval I. Okay. So again, IVP is what's called an initial value problem. We are also going to be solving what are called boundary value problems. So if instead your conditions look like the following. If you have y of x naught is equal to y naught, and then y of x1 is equal to y1, and so on and so forth. This is called a boundary value problem. Normally denoted BVP. So there's 2 things that you should notice, 2 big differences. In an initial value problem, the conditions you are given are always at the same value of x. Whereas in a boundary value problem, different value of x each time. The other thing that you should notice is in an initial value problem, we have y, and then we have the first derivative, and then the second derivative, and so on and so forth. Whereas in a boundary value problem, it's always y. Every condition is based on y. Okay, so we've talked about before, a lot of the times we don't necessarily care about what the solution is, but is there a solution? So sometimes we're not actually going to be solving, but we just want to know, is there a solution? And then furthermore, is the solution unique? So that's what we're going to talk about next. Okay, keep going. Okay, so here is the first theorem we're going to talk about. This theorem discusses the existence of unique solutions. Okay, here's what the theorem says. Let an of x, an minus 1 of x, all the way up to a1 of x, a0 of x, and g of x all be continuous on an interval I with a n of x does not equal 0 for all x that are in the interval. So that's what those last three symbols mean, for all x that's an element of that interval. If x naught is an element of that interval, then a solution to the initial value problem above, so the one we already wrote, exists and is unique on that interval. Okay, so in order for a solution to exist and be unique on that specific interval, really two main things have to occur. All of those coefficients have to be continuous on the interval. So that's the first thing that you're going to check. When you have your initial value problem, are all of the coefficients continuous on the interval? And then the very first coefficient cannot be 0 for all x that are in that interval. Okay, so we're going to see two examples using this theorem. Here's the first one. Y equals 3e to the 2x, add e to the negative 2x, subtract 3x, is a solution to the following initial value problem. Y double prime, subtract 4y is equal to 12x, with y of 0 is equal to 4, and y prime of 0 is equal to 1. Okay, so this theorem applies only to initial value problems, not to boundary value problems. So we need to make sure that this is an initial value problem. You're told it, but we should be able to check this. What you're looking at is I have y at some point, and then I have the derivative at that same value. That's what tells us that we have an initial value problem. From above, we see we need to look at all of the coefficients. All of the coefficients. So here's what you're looking at. This is a(n) of x, or a2 of x. There's our a1 of x, and here is our g of x. So the first thing that we say is that 1, negative 4, and 12x are all continuous on the interval negative infinity to infinity. Then we need to make sure, like in blue, the initial coefficient is not 0 for all x. Well, our initial coefficient is that 1. That 1 is never going to be equal to 0 for all x from negative infinity to positive infinity. So what that tells us then is there exists a unique solution containing x equals 0 on the interval negative infinity to infinity. And the 0 comes from those initial conditions. So, therefore, the solution we were given, y, is unique. Aaron?
We have like a little arrows, the one under y double prime, what does that say? The a n of x?
Yeah. So in this case, it would be a of 2 since it's second order, but yeah. Okay. Let's look at another example where the solution is not unique. So here is the next one. We have x squared y double prime, subtract 2x y prime, add 2y is equal to 6. And that has the solution y equals cx squared, add x, add 3. And so we want to know, is that solution y unique? So first thing that we're going to do, like we did before, we're going to look at all of those coefficients. and we see that x squared, negative 2x, 2 and 6 are all continuous for all real numbers, negative infinity to infinity. Why then is that solution y not unique? Any idea? The continuous requirement is met. So what is not met?
X squared equals 0.
There you go. That first coefficient equals 0 when x is 0. So any interval that contains x equals 0, the solution is not guaranteed to be unique. So here's what this tells us. This violates the existence theorem. So y is not guaranteed to be unique. Now, that does not mean that y is not unique. It could be unique, but we don't know for sure. So that's the existence and uniqueness theorem. Okay, so that applies to initial value problems. So the next question is, what do we do with boundary value problems? So that's what we're going to talk about real quick. Here's the idea with a boundary value problem. When you solve a boundary value problem, you're often going to come up with a family of curves. Something like this. So when you solve, you will often come up with a family of curves that satisfy that differential equation. But then you're given your conditions. So you're given these points x0, y0, x1, y1, so on and so forth. So you're looking for the specific curve that meets all of those conditions. Those are just points. So this might be the point x0, y0, and maybe this is the point x1, y1. So that's what you're looking for, is you're looking for the one curve that goes through all of those points. Okay. Here's an example of a boundary value problem. Consider the boundary value problem y double prime add 16y is equal to 0 with conditions y of 0 is equal to 0 and y of pi over 2 is equal to 0. And I'm going to tell you that the solution is y equals c1 cosine of 4x plus c2 sine of 4x. We are going to find C1 and C2. Okay, if we start with the first condition, y of 0 is equal to 0. We're going to substitute into the solution that we have. So then, we end up with 0 is equal to C1 cosine of 0 plus C2 sine of 0. Cosine of 0 is 1, sine of 0 is 0. So that gives us then C1 is equal to 0. So then if we try y of pi over 2 is equal to 0, we get 0 is equal to C1 cosine of 2 pi plus C2 sine of 2 pi. Well, sine of 2 pi is 0. Cosine of 2 pi is 1. So again, we get C1 equals 0. What that tells us then is that C2 is arbitrary. Our solution is y equals C2 sine of 4x. So if we look at what's happening, we have our point 0, 0. We have our point pi over 2, comma 0. And if we were to graph sine of 4x, it goes like this. So that's a solution. This is a solution. That C2 is only affecting the amplitude. So solving this problem shows us that there are infinitely many solutions to this boundary value problem. Okay, so here's what you need to know. For a boundary value problem, if conditions are met for existence and uniqueness, like they were for an initial value problem, there could be several solutions, like in the example above. There could be one unique solution, or there could be none. So there is no way to tell for a boundary value problem if there is a solution and if it's unique besides solving the problem. So putting it into writing, the difference between an initial value problem and a boundary value problem have to do with the conditions. An initial value problem, all the conditions are at the same value of x. For an initial value problem, there are only conditions for the solution curve. Okay, that is the first topic for today. Questions before we keep going? Okay, next idea is we are going to talk about what is called a homogeneous equation. And you're like, I've heard that before. This is a different one. Okay, so when I say homogeneous here, it does not mean the homogeneous that we've already talked about. There are two different kinds. Here's the first one. an of x times the nth derivative plus an minus 1 of x times the next derivative, all the way down to a1 of x dy dx plus a0 of x times y is equal to 0. Okay, if you have all of the left side the same, but this time we are equal to some function g of x, that's called a non-homogeneous linear differential equation. So, this first one with the 0 is called a homogeneous linear differential equation. The second one that I was too lazy to recopy the left side to, all that changes is what's on the right side. This is a non-homogeneous linear differential equation. There is a huge difference when you are solving the two. So if you're equal to 0 versus being equal to g of x, big difference in the solving. In order to solve a non-homogeneous linear differential equation, you first need to solve the associated homogeneous linear differential equation first. So we would solve the homogeneous one and then use that to solve the non-homogeneous one. Now, some basic assumptions that we are holding here. We are assuming that all coefficient functions ai of x, so an of x, an minus 1, a1 of x, a0 of x, all of those, and also g of x are continuous. And we are assuming that an of x does not equal 0 for all x in the interval. Okay. Next thing we're talking about is what's called a differential operator. Or sometimes they're called differential equations, obviously. Here's what you need to know. A capital D indicates differentiation. That D is often called a differential operator. So for example, if you see D of cosine of 4x, what that's telling you to do is take the derivative of cosine of 4x. And so we would get negative 4 sine of 4x. If you are taking d of dy, that's saying take the derivative of y and then take the derivative again. So that is the second derivative of y. You might see something like this, d plus 3 applied to cosine of 4x. What that means is d of cosine of 4x plus 3 times cosine of 4x which is negative 4 sine of 4x and then just 3 cosine of 4x. So this is notation that we're going to use later. What you need to know is that we can write any linear differential equation with differential operators. So let's say we have the equation y double prime, add 5y prime, add 6y is equal to 5x minus 3. The way we would write that with a differential operator is d squared of y plus 5 dy plus 6y is equal to 5x minus 3. Those are equivalent. Okay, so the last item that we need to talk about today, the most important thing that we're going to talk about today, is the superposition principle. So we're going to cover what is the superposition principle, why it's so important or so powerful, and then we're going to look at the proof. So here's what the superposition principle says. Let y1, y2, all the way up to yk be solutions to some homogeneous linear differential equation I marked that as star 1 earlier. So that was your differential equation that was set equal to 0. So we have these solutions on some interval I. Then y is equal to c1 y1x plus c2 y2x all the way up to ck ykx is also a solution. Okay, so we're going to talk about, first of all, the proof of this, and then look at an example of why this is important. So let's start with the proof. For simplicity case, we are just going to consider the case where n is 2. Okay, so let y1 of x and y2 of x be solutions of a homogeneous linear differential equation of order 2. So that would be a2 of x, y double prime, add a1 of x, y prime, add a0 of x times y is equal to 0. And we are going to let y be equal to c1 y1 of x plus c2 y2 of x. Okay, so we know y1 and y2 are solutions, but we also have to show that y is a solution. So what we're going to be doing is we're going to be plugging y into our differential equation. So we're going to need the second derivative and the first derivative. So we can probably, hopefully, do that in our head. So what we're going to do is we're going to plug that y into the equation that we have. So our differential equation becomes then a2 of x times the second derivative of y, which is going to be c1 y1 double prime of x plus c2 y2 double prime of x. Then we have a1 of x multiplied by c1 y1 prime of x plus c2 y2 prime of x plus a0 of x times y, so that's c1 y1 of x plus c2 y2 of x. Now, we don't know that that's equal to 0. We can't set that equal to 0 because we don't know that y is a solution of the differential equation. That's what we're trying to prove. So we want this equal to 0. So what we're going to do is we're going to rearrange it. If we take all of the y1s together and then all of the y2s together, this is what we're going to end up with. We're going to end up with c1 times a2 y1 double prime of x plus a1 of x y1 prime of x plus a0 of x y1 of x plus c2 times a2 of x y2 double prime of x, add a1 of x y2 prime of x, add a0 of x y2 of x. Now, initially we might be asking, why is that helpful? Why is that helpful to us? Well, we know that y1 is a solution. We also know that y2 is a solution. So both of those are equal to 0. So we end up with our differential equation equal to 0. So what does that do? That shows us that y is equal to c1 y1 of x plus c2 y2 of x is also a solution of our differential equation. Okay, before we look at the last example from these notes, we have a few quick remarks about the superposition principle. First remark, a constant multiple of y equals c1 y1 of x of a solution y1 of x is also a solution. So if you have a solution of a homogeneous linear differential equation, then Any multiple of that solution will also be a solution. And then a homogeneous linear differential equation, so again, one that's set equal to 0, which I denoted with star 1, always possesses the trivial solution y equals 0. Now, we've talked about before, oftentimes we don't care about the trivial solutions or trivial solution, however many there are. We care about finding the general solution, but it's just something for you to know. Last example for these notes. Suppose y1 is equal to e to the x, y2 is equal to e to the 2x, and y3 is equal to e to the 3x. All satisfy the differential equation, third derivative with respect to x, subtract 6 times the second derivative, add 11 times the first derivative, subtract 6y is equal to 0. Okay, so first thing I want us to notice is this is a homogeneous linear differential equation because it's set equal to 0. Okay, so the superposition principle does apply here. If it was not a homogeneous linear differential equation, we couldn't use superposition. So what this is telling us is by the superposition principle, y is equal to c1 e to the x, add c2 e to the 2x, add c3 e to the 3x is also a solution. Okay, you might be saying, so what? Why do I care? Well, this is incredibly more powerful than just listing 3 solutions. And here's why. The y1, y2, and y3 are all, this is not a math term, but it's my term, they're all oddball solutions. They're just one-offs. But y could be the general solution. So this y could be the general solution, not necessarily, but it could be.